members, a 1/2 inch and a 3/4 inch, connected together using a bolt and a nut. So these two plates are clamped together with a washer faced 1/2 inch 20 UNF, and I would say that this length is not correct. It's given here as 1.5 inch, but anyway, we're not gonna need the length, but we are gonna look at the grade of the bolts. It is SAE grade 5 bolts, each with a standard 1/2 N steel plain washer. 1/2 N steel plain washer. So if I want to learn about the washer that is going to be used, I'm going to be going to table A32 that gives us the basic dimensions of American standard plain washers. And if I go here to 1/2 N for the fastener size, I get the washer size is 0.5. I get the inner diameter, I get the outer diameter, and I get the thickness of 0.095, which is what we're going to need. Question?
I know this is not in the future, but on the exam, I think it's going to be opened up because it sounds like a lot of tables.
Correct. Open book, most likely. Right. So the question was about the exam, and the exam is going to be most likely open book if the tables are not going to be provided. Okay. We want to determine the member spring rate or member stiffness Km if the top plate is steel and the bottom plate is gray cast iron. We want to use the method of conical Frusta to determine the member spring rate Km if both plates are steel. We want to compare that to the spring rate calculated using the finite element model, which is equation 823, and compare what we get from C to B. And we also want to determine the bolt spring rate KB. Okay, so this covers the topic that we just went over. By the way, if you were interested in finding the total length of the bolt that is required, I will be looking at the grip length. So I look here, I have a 0.095 and a 1/2 and a 3/4, and I still need to add the thickness of the nut plus 1 or 2 threads to extend beyond the nut. So if I want to find the thickness of the nut, I will be going to table A31, where I look at a nominal size, and I come here to 1/2 inch, and I'll be given the width. For a regular hexagonal, I have a height or a thickness of the nut that is 7/16. For a thick, I have 9/16. For a jam, I have 5/16. So these are the standard dimensions of a nut that will go within 1/2 inch. Okay. So if I look at what I am given, I am given here the two members. Now, the top member is made of steel, and the bottom is made of cast iron. And under the head, I have this washer, and this washer is also made out of steel. So it's a steel washer. So now if I look at my grip length, that would include, if I want to calculate the grip length, this is equal to the 0.095 plus a 0.5 for the steel plus the 0.75 from the cast iron. So I'm looking here at a total of 1.345 inches for my grip length. Remember that my frustum extends from under the head, the bolt head, all the way to the washer. And I am interested in the midpoint because this is where I get here my Frusta from the top and from the bottom. They're gonna meet at midpoint. So my midpoint is at L/2. And this L/2 would be 0.6725 inches. Now, when I look at the 0.6725, this is extending into the steel members and partially into the cast iron. So I need to understand exactly or find the thickness of my first frustum that is made out of steel, right? The thickness of my first frustum that is made out of steel. So I want to look at this thickness here, right? So if I know that half the grip is 0.6725, and we know that the thickness of the cast iron is 3/4 of an inch. So clearly we can see here that the portion within the cast iron would be the 0.75 minus 0.6725. So this is how I got my 0.0775. Okay, so I would be doing like 0.75 minus 0.6725. I get here this 0.0775 inches. So now if I subtract 0.0775 from 0.6725 here, I will get the thickness of my first frustum to be equal to 0.595. So we're really using the geometry extensively. The washer face of the bolt is 1.5 times the diameter. So I have here a 0.75. Next, I want to find for my second. So if you look here, I have 1, I have 2, and I have 3 Frusta. For each frustum, we're going to be calculating a spring rate. So I'm going to have a K1, a K2, and a K3. Okay. Now for K2, I'm going to need this diameter, which is shown here as 1.4375, right? So how do I calculate this 1.4375? So this is T2, is 0.0775. Now, in order to find the uppercase D2, I will be using the 0.75 here, and then add using alpha here equal to 30 degrees, right? So I will be adding to that twice 2 multiplied by the thickness of the first frustum, which is 0.595. So this is T1. Multiplied by tan 30 degrees or tan alpha. So when I do the numbers here, I get 1.437. So this is where I got my D2 from. Since I'm looking at the geometry, let's also identify for layer 3. What is D3 for layer 3? No, wouldn't that be simply where the 1.527 is actually, because for the third frustum, I can go from the bottom here all the way to the top, right? Looking at it reversed. So for 3, I will be using a 0.75. Which is the nut face, right? And I'll be using a T3 that is equal to, for 3, I have half the grip length, L/2, which is 0.6725 inches. So now we're ready to do some calculations. And for part A, I will be using equation 820. So this is equation 820. And you see in equation 820, what is required is a modulus of elasticity, lowercase d and uppercase D, and the thickness. And we have that for all the 3 different frusta that we have here. So when I use equation 820, I'm going to calculate a K1 that is equal to 0.5774 multiplied by pi multiplied by E, which is 30 times 10 to the power 6, multiplied by the lowercase d, which is 0.5, divided by ln, and inside that ln, we're going to have a 1.155 multiplied by the thickness, which is 0.595 for T1, plus the uppercase d, 0.75, minus lowercase d, which is 0.5, multiplied by uppercase d, 0.75, plus lowercase d, which is 0.5, divided by 1.155 T lowercase t, which is 0.595, plus uppercase d, 0.75, plus 0.5, multiplied by 0.75 minus 0.5. So when I do the numbers, I find K1 to be equal to 30.8 times 10 to the power 6. And the units for the spring constant or spring rate would be pound per inch. Now we're going to apply equation 820 for 2. So for K2, I'm going to get 0.5774 pi times. Now for 2, what material is used for 2? Cast iron, right? So my modulus of elasticity, E, is no longer going to be 30, but it's going to be, for the modulus of elasticity for cast iron, I'll be looking at 14.5. So I have here 14.5 times 10 to the power 6. Oops, sorry. Multiply by D is still 0.5. Divided by ln and we have the 1.155 multiplied by the thickness, and now I'm using T2, and for T2 I'm using 0.0775. Plus, I have here uppercase D, and the uppercase D2 we found to be 1.437 minus lowercase d, which is 0.5, multiplied by d plus d. So I have 1.437 plus 0.5 divided by 1.155 times 0.0775 plus 1.437 plus 0.5 multiplied by 1.437 minus 0.5. Now, of course, for an equation like this, it would make sense if you just program it so you don't do mistakes, and then you just input your lowercase d, your uppercase d, your t, right, and e, and you will get the answer. So when I do the math, I get here 285.5 times 10 to the power 6 pounds per inch. So if you repeat a third time, I have here D3 and T3. So similarly, we can do the math for K3, and you're going to find that K3 is equal to 14.15 times 10 to the power 6 pound force per inch. Be consistent. So now I have K1, K2, and K3. In order to find Km, I will use my springs in series. 1 over Km is equal to 1 over 30.8 times 10 to the power 6 plus 1 over 285.5 times 10 to the power 6 plus 1 over 14.15 times 10 to the power 6 So when I do the math here, I'll find that Km is equal to 9.378 times 10 to the power 6 pound force per inch. So here I'm using two different materials, steel and cast iron, and I'm using an apex angle alpha of 30 degrees, and we find Km, the stiffness of the members, to be 9.378 times 10 to the power 6. Our next question is to find if the two plates were made out of the same material. We want to find the member stiffness using equation 822. So here is equation 822. So for part B, if both plates are steel, using equation 822. Now, when I look at 822, what I need is E. So I'm going to use the 30 times 10 to the power 6. D is 0.5 inches. Right? The grip length, we already calculated the grip length L to be 1.345. Okay. And this is all what I need for equation 822. So using equation 822, Km, I have here 0.5774 times pi times E, 30 times 10 to the power 6, multiplied by D, which is 0.5, divided by 2 ln 5 multiplied by 0.5774 times 1.345 plus a 0.5 times 0.5 divided by 0.5774 times 1.345 plus 2.5 times D, which is 0.5. So doing the math, we find that Km, if all is steel, is 14.64 times 10 to the power 6 pound force per inch. Of course, if I compare that, when I use steel and cast iron, you see here the stiffness of the member is almost 1.5 times when I had a plate made of steel and the other one made of cast iron. For part C, we are going to use the finite element model equation 823. Where Km is equal to E times D multiplied by A, the exponential of B D over L. Oops, sorry, let's see. So I simply copied here equation 823, rewrote it to give me Km. So equation 823. Now we want to use the table 88, to find A and B. So use table 8.8. We find A, again, I'm looking for steel. So I find A to be 0.78715 and B to be equal to 0.62873. So now when I apply equation 823, I will have Km then equal to E, which is 30 times 10 to the power 6, multiplied by D, which is 0.5, multiplied by 0.78715 times the exponential of 0.62873 times D, which is 0.5, divided by L, which is 1.345. When I do the math, we find Km here using the finite element model to be equal to 14.92 times 10 to the power 6. Now, if I compare this to what I found using the Frusta method, I have here 14.92 and we have here 14.64. So the difference is really very small. And finally, part D. Just to remind you, in D, we were asked to find the bolt stiffness. So D, we asked to determine the bolt spring rate KB. We have equation 817, KB is equal to AD times AT times E divided by AD LT plus AT LD. So if we follow the procedure that we discussed earlier, given in table 8.7, right? So I have a bolt and a nut, a bolt and a nut. So in order for me to find the threaded length LT is equal to twice the diameter of 0.5 plus a 0.25. So I get a threaded length of 1.25 inches. So the unthreaded portion, LD, is equal to the total length minus LT, so uppercase LT. Now the total length, even though I have doubt that this works, was given as 1.5 minus 1.25. I get an unthreaded portion of 0.25 inch. So by the way, we're referencing this here. So I'm looking now at an unthreaded portion of 0.25. Now we want to find the threaded portion within the grip. So yes, I have here an LT of 1.25, but we need to find a lowercase LT, the unthreaded, the threaded portion within the grip. And this would be equal to, the grip is 1.35. So it is the grip minus the unthreaded portion. So the grip is 1.345 and the unthreaded portion is 0.25. So I find here 1.095 inches. For a bolt, D equal 0.5, I can find A, the nominal area, AD, as equal to pi over 4 times D squared times 0.5 squared. And I will get here a 0.1963 square inch. In order for me to find the threaded area, I'm going to use table 8.2. I'll find the threaded area, the tensile area, and I'll find that, of course, it has to be smaller than this. I'll find this to be 0.1599 square inch. This is square inch. Now I'm ready to apply my equation for the spring rate. So, I'm sorry, for the bolt spring rate. So KB is equal to AD, which is 0.1963, multiplied by AT, 0.1599, multiplied by E for steel. I'm going to use 30 times 10 to the power 6, divided by AD, 0.1963, multiplied by LT, which is 1.25, plus AT, which is 0.1599, multiplied by LD, which is 1.095. I do the numbers, I get a KB that is equal to 3.69 times 10 to the power 6 pound force per inch. Just to put things in perspective, how does the stiffness of the bolts compare to the stiffness of the members? It's a lot less. Like 30–40%, right? Compared to the members. Now, when an external load is going to be applied to the connection, which of them is going to carry more of the load, of the external load? How does the load get distributed if we have two springs in parallel? Now, if you don't think of these things, I think this is going to be tedious and boring. But really, I mean, we're just, and you're going to do mistakes. But if you make sense out of what you're doing, I think you're going to enjoy it more and become a better designer. So if I'm looking at this be modeled using two springs in parallel, right? So I have the bolts and I have the material. And as I apply an external load P, this P is going to be handled by the bolt and the material. Remember, the bolt is in tension. And the members are in compression. this external force is in tension. So it's going to further stretch the bolts. And it's going to try to uncompress the members in the grip. Okay. And this is what we're going to be discussing next week on Tuesday, how to come up with a good design to make sure that the members, when the connection gets loaded, the members do not lose the grip. Because if I separate, if I uncompress too much and I lose the grip, I lose the stiffness of it. And everything is going to be handled by the bolt. And this is why many of the connections would fail if this occurred, right? So we rely a lot on the compression of the members within the grip to carry this external load. We do not want the load to be primarily handled by the bolts. Now, simply when we get this model here, an external load is applied. How do we find which load goes to which? Basically, delta, the extension of this bolted connection, is going to be equal to delta. This external force is going to cause an extension that be measured by the portion that goes in the bolt divided by the stiffness of the bolt. And the elongation of the material, or the same elongation delta, may be measured by the force going into the material divided by Km. Now, these two are equal. So I can relate the load going into the material to the load going into the bolt by Km over Kb multiplied by Pb. So if Km is like 3 times as much of that of the bolt, so the material is going to take, right? So this is like, if this is 10 and this is 3, it's going to take more than triple what the bolt is seeing, Now, an important question is, in order to get the stiffness in the member, I need to tighten my nut. So how far do I tighten?
Usually, isn't it stretch, but stay in the plastic area so that it doesn't.
Yeah, we definitely do not want our bolt to yield, right? So in order, when we look at bolt material, and I know we're running out of time here, so I'll finish in a second. There is a proof load, which is the maximum load that the bolt can withstand without a permanent set or a permanent deformation. The recommended preload is 75% of the proof load. Okay. So this is the recommended one. So then it will allow it to handle the additional PB, right? That's going into the bolt. Okay. We'll talk about this more when we meet again next Tuesday. I think for now you have everything you need. You only have 3 problems. I think you can get it done by the weekend. I made the deadline Tuesday, but please don't wait to the last minute, because as you are seeing, when we keep waiting on the homework, even to the very last minute, we still need more time, right? And we discovered that we have questions. So I urge you to please start working on the homework immediately. You have everything you need to complete homework number 10. I'll see you all on Tuesday. Have a great weekend.